Algorithms teach computers to make decisions. Today, we compare three strategies: greedy, backtracking, and branch and bound. A greedy algorithm takes the immediate best path. Backtracking explores and retreats at dead ends. Branch and bound uses math to rule out expensive paths. Let's test greedy logic with the fractional knapsack problem. Imagine a bag with a hard weight capacity of 60. You want to maximize the profit inside. We start with this table showing items, weights, and profits. A greedy algorithm seeks the most value per unit of weight. We calculate the profit-to-weight ratio for each item, then sort the list, placing the highest ratio items at the top. Now it executes. It grabs the top item and puts it in the knapsack. It repeats this choice, taking the next best full item until the remaining space is too small to fit the next one. Instead of leaving empty space, it maximizes the final capacity by taking a fraction of the next item. By scaling its weight and profit proportionally, we perfectly hit the 60 capacity and reach a maximum total profit of 230. Greedy algorithms excel when local optimization leads directly to a global solution, like building a Huffman coding tree for data compression. But if a current choice severely limits future options, greedy logic breaks down. When future constraints make a greedy approach impossible, we have to test paths and retreat when they fail. This brings us to backtracking. This diagram represents the 4 queens problem. The rule: place 4 queens on a 4x4 grid so none can attack each other. We place queen 1 top left, projecting its attack paths. Queen 2 goes in the first safe square in row 2. Now check the third row. Where can queen 3 go? Every square is currently under attack. Hitting this dead end, the algorithm backtracks. It steps up, moving queen 2 to the next valid square. This recalculation opens a safe square for queen 3. Backtracking operates purely on hard rules. It explores a path deeply, and the exact moment a rule breaks, it prunes that branch and reverses course. But what if you are trying to find the cheapest path, not just a valid one? Branch and bound optimizes this process by estimating the minimum cost of a path before exploring it. Here is a matrix representing the worker job assignment problem. We determine the absolute lowest baseline cost by subtracting the minimum values across the rows and columns. This calculated total gives us the starting lower bound for our root node on the right. Next, the algorithm creates branches, calculating separate lower bounds for assigning worker A to job 1 or job 2. If a branch's estimated cost exceeds a known complete path, exploration stops immediately. It tunnels straight to the final assignment, yielding the minimum cost of 13. Branch and bound relies on mathematical guarantees over blind guessing. It drastically reduces computational waste by pruning paths that are mathematically proven to be suboptimal. Comparing these decision trees side by side reveals key differences. The 4 queens backtracking tree is tall, driven by depth-first navigation, while the worker job tree expands horizontally via least cost paths. Backtracking halts upon an invalid state. Branch and bound halts when a cost limit is exceeded. This table synthesizes the 3 approaches. Greedy algorithms rely on local optimums for problems like the fractional knapsack. Backtracking uses depth-first logic for constraint puzzles like n queens. Branch and bound uses least-cost logic for optimization tasks like job assignments. Keep this reference handy. Mastering algorithm design is not a matter of memorizing code syntax. It is about analyzing the mathematical constraints of your problem and choosing the right navigational strategy to solve it.